Thank you very much for inviting us to come and talk a bit about what we're doing in quantum sensing. This is a wonderful time in the field and a nice extension actually at QTB, moving beyond just quantum computing and now looking at quantum sensing and communications, especially given the fact that these modalities of sensing and communications now have advanced quite a bit and are in the process of transitioning into the field. We will today share with you a bit of what we've done at Infleqtion to advance quantum RF sensing and to take it out of the lab and now into the field to do our first demonstrations and evaluations of this quantum RF receiver. We're also thrilled to publicly announce that we now have a partnership with L3Harris, where we are collaborating on the development of quantum technology with the goal of transitioning this to L3Harris customers within the next 2 to 3 years.
No, so just to introduce myself, we've been really excited about the partnership that we have, and we're going to go through our technology, but it's been a great opportunity to work together on this. So yeah.
So I want to start off with a few what ifs, kind of get you thinking a bit about this quantum technology and start to maybe challenge the way you think about communications and sensing, because it is often the case where we try to find ways to solve problems that already are being solved by classical technologies, and those are typically done in a way which are constrained by classical technology itself. Quantum begins to open up new tools, if you like, that can be applied to address these problems. In some cases, these are very disruptive. So this simple question of what if an RF receiver could be physically small, one size, and yet operate across a broad range of frequencies? What if it were bound by quantum sources of noise, not classical sources of noise? And what if you could tune that sensor, from very low frequencies at, say, tens of hertz out to terahertz in frequencies, and at the same time also have sort of innate capabilities in the sensor that is inherently resistant to the effects of interference, whether that's congestion and or contention? How would that change the way you imagine future systems will be designed, whether those are sensing systems, whether those are communication systems, and maybe even more importantly, network systems? How would that change your perspective on the use of spectrum, as well as the utilization of that spectrum? How do you optimize that for these given purposes? And then it's a really interesting question to also think about the physical level of security that can be enabled now through the use of these types of sensors, how you can protect information by broadly spreading it across bands, not within bands, but broadly across the entire electromagnetic spectrum. So it turns out there's a class of sensors that are capable of doing this, and these are based on Rydberg atoms. We refer to this as quantum RF, and we use these Rydberg atoms, which are just highly excited states of atoms. It could be of molecules as well, typically just high N, high L states. And we exploit two characteristics of these gases when configured appropriately. One is electromagnetically induced transparency and or absorption, and outlet towns. Both of these are atom photon types of processes that occur within the atoms, and they result in quantum mechanical interference within the atoms themselves. And those are the mechanisms by which we can transduce information in an RF signal, eventually onto an optical carrier to do back-end optical detection. These sensors, and if you're familiar with what's been published in the literature, there are groups around the world that have demonstrated tunability all the way down to tens of hertz and all the way up to terahertz in frequencies using these devices. Typically, the only thing that limits you in tuning is really your test equipment. Sensitivity today is approaching the standard quantum limit, meaning that we're at a point where these sensors, without any type of cryogenic cooling and any special engineering, classical engineering, are capable of performing right at that fundamental limit of performance. And with additional enhancements, may move beyond that to outperform classical receiver systems, the best that exists today. Now, what's interesting too is instantaneous bandwidth. As we know, in a communication system or in a sensing system, bandwidth is as important as tunability is, as well as sensitivity is. And today, just using CW pumping approaches, we can achieve up to about 10 megahertz of instantaneous bandwidth. But with more advanced techniques that have been developed now by L3Harris and now in collaboration with us, we're going to be able to extend that. We're looking to extend that instantaneous bandwidth limitation from 10 potentially out to about 100 to several hundred megahertz of instantaneous bandwidth. And if it helps, it's worth thinking like thinking of these systems kind of like RF photonic systems. In the last 20 years, there's been some amazing developments in the use of optical carriers, electro-optical modulators, and antennas to be able to transduce signals into the optical domain and then to process them using optical techniques. What's different here, however, is we don't have antennas. There's no need for an antenna. There's no need for analog filtering. There's no need for LNAs and mixers. All of those functions are actually accomplished through atom-photon interactions in the gas. And that is why we are physically small. And that is also why we can operate at levels of sensitivity that are beyond where traditional classical receiver technology is today. So to take that just a bit further and to show you what this really means, here at the top you'll see on the left is where we start. We use lasers. Now we don't just use one, we typically use 2 or 3 or more lasers in order to pump the atoms into these states. And that's needed. It's needed because 1, you want to get into these highly excited states, and 2, you want to exploit geometry in these cells in order to be able to get subdoppler performance. When you do that, now what you see on the right is what we call EIT. Now you can think of EIT in a variety of ways. You can think of it as anti-absorption, or as a dark state which is created by the use of optical pumping of these atoms into these excited states. But when these atoms are in these excited states, these ripper states, the atoms that are excited are no longer essentially in the volume. They're not available to absorb photons of the probe frequency. And so that frequency will typically pass through the cell uninterrupted. And it results in what you see there is an anti-absorption curve, EIT. Now that's pretty interesting because it has a lot of really good characteristics. It has a large signal-to-noise ratio. It has a really, really good line width associated with it, which is typically an atomic line width. And so it's an absolutely fantastic carrier. But what's more interesting is what happens when you illuminate that cell with an RF signal of any frequency. I shouldn't say RF, but really electromagnetic signal, any frequency that you have interest in. It results in transitions, if the atom is tuned appropriately, to other Rydberg states. And that means that you've created new pathways within the atom to de-excite, and you get quantum mechanical interference within the atom, which results in a splitting of that EIT peak into 2. Now, if that were a time-varying signal, you'd actually see those 2 sidebands act like sidebands. That is, they carry the information that is transduced from that RF signal onto this optical carrier. The important thing here, as I said, is we're doing this without antennas. We're doing this without LNAs and without mixers. So this is what it really looks like. So everything you see in that dashed box there on the left is what a normal, classical, traditional RF communication system would look like. There's an antenna, there's a feed structure, there's an analog receiver which has analog filtering in it, LNAs, and mixers. All of that now is effectively replaced with a small device. Now this is not the smallest we've created. We've actually integrated down to about 1 cubic centimeter. That means all the atomics, all the micro-optics and electromagnetics is now 1 cubic centimeter in size. Those devices are fiber coupled, so you can place one of these devices wherever you like at distance with the back-end photonics and electronics wherever you need it to be. This happens to be, I think, a very interesting variant of that, and this is actually a 6-channel version. The reason I show you this is because this is what starts to change your thinking about how to use quantum RF to change communications and sensing systems in the future and networks. In this case, each one of these cells, shown as different colors, is independently tunable across nearly the entire electromagnetic spectrum. Okay, again, no antenna. You can tune those all to the exact same frequency, and you can coherently combine them like you do in a phased array to get added gain. You also can use them to do direction finding. You could also tune each one of those to a consecutive portion to different frequencies, but ones which are consecutive in the electromagnetic spectrum in order to create a larger swath of spectrum for ingest within that receiver. Now that's one mechanism to increase the instantaneous bandwidth of these receivers. And then probably the most interesting configuration is where you tune each one to a non-contiguous portion of the spectrum. So imagine for a moment that that top cell, that channel, that full receiver system now is tuned to an IR band to pick up heat signatures. The one below that is tuned to millimeter, 100 gigahertz or above, right, to do high resolution imaging on targets of interest. The one below that is tuned to K-band for satellite communication. The one below that to L-band for GNSS. The one below that to frequencies from MF through UHF for tactical communications. And the one below that for operation even below that frequency. Right, all within one single device, simultaneously performing all those functions. It is true convergence, and I think it's the first time, at least in my career, over the last 30 years that I've seen any RF technology that's been capable of bringing convergence across all these frequency bands. And to exemplify that, here we're showing what can be done. one single channel of that device, right, could actually replace the receiver systems, antennas and receivers in every single one of these communication systems. Everything from man-pack radios out to fairly sophisticated and large-scale satellite communication systems. But what's more exciting is that a multi-channel variant of this could do all of that. One single device actually accomplishes all of those functions, and that device is physically small. So whereas in the past, you couldn't have flown, let's say, an HF receiver system on a microsat, right, or on a small UAV. Well, you could do that today. And at the same time, you could access the remaining portion of the spectrum by using this one single receiver. So that's pretty exciting. A lot of work's been done, not only by us, but others around the world. But for us, what's been most exciting is this year, we have succeeded now in integrating this down, basically creating a portable version of this type of receiver system that can be brought to the field. And we did that. We did it in September in collaboration with the Army as part of the Army Net ModX event. As you can see here in the upper left, it was 2 small half racks, mostly 1 half rack of photonic equipment that's been integrated down, and a little bit spilled over into another, which is the electronic piece of it. And then down below are 2 sensor heads. Inside each of those radomes, it's a small little sensor. Right? It's a little vapor cell that's been highly integrated with all the micro-optics and electromagnetics. And each one of those acts as a full receiver system, tunable across nearly the full spectrum. And 2 of them are placed on this post because we wanted to be able to do direction finding, angle of arrival estimation. What we succeeded in doing at this event for the first time is we demonstrated functionality. We demonstrated the ability to tune across a broad range of frequencies, to be able to pick up unmodulated CW signals, but also modulated signals, AM, FM, PSK, and QAM signals that were transmitted by the Army. Beyond that, though, I mean, we were the only company to do this. We took the system and we decided to see if we could actually integrate with 2 Army systems. One was an EW system, and the other was a tactical communication system. We took the output of the photodetectors, which is the baseband RF signal. We used that, we removed the antennas on these 2 systems, and we fed that through the antenna port, through the receiver system. In the case of the EW system, we demonstrated improvement in performance. So by replacing their front end, bringing ours in, we demonstrated improved ability to detect signals of interest across that range of frequencies that they were interested in. Now, maybe more impressive than that is the integration with the handheld PRC-148B radios running SINGARs. So SINGARs is a communication waveform, and again, this is ciphertext, so there's transec, there's ComSec running across this, and it turns out to be a hopping waveform. So we ran that as the communication protocol, had 1 radio acting as a transmitter. The receiver system was another radio where we coupled it into the receiver port and fed the signal. Now, while it's a bit of a cheat to say, well, we went through the receiver system, what's important to know is that there was no degradation of performance as a consequence of our front end, right? By replacing their front end antenna system, we provided a very clean signal in amplitude, phase, and frequency that they were able to detect, they were able to demodulate and decode and recover the information, in this case, voice, that was transmitted across that channel. So this is a very significant development. For the first time, we've now taken a quantum sensor, in this case, quantum RF, and we've transitioned it from the lab into the field. And now, with support with L3Harris, we're taking it the next step. We're going to begin to develop and advance it for L3Harris customers on the DoD and the Intel side. And it's a perfect opportunity then now to transition to Chris, who will talk about what some of those challenges are.
All right, thanks, you guys. So, so as many of you have also probably done, once you take this, amazing, technology and these capabilities, you start talking to customers about it. In general, what do they want? They're looking for ways that you're going to improve their performance, improve their lives. So as we started talking with our customer set, specifically, these are the challenges that ended up getting brought up. And so there's sensitivity, there's swap, and these are all things that Infleqtion has been revolutionizing. So one of the major challenges also that we have been working on for some of our communication side as well as some of this Rydberg atom was increasing the instantaneous bandwidth. And so as William highlighted, we've got to get beyond the 10 megahertz that we're able to do today and be able to expand beyond that. So we ended up, some of our scientists ended up coming up with this spatiotemporal multiplex receiver configuration. We wrote a paper on this. I meant to have the link down below, but if anybody wants it, let's touch base afterwards and get you the link. But specifically with the continuous wave solution, you end up not being able to, you're limited by the latency and the low sampling rates. So the approach that our team took is you take that continuous wave, you divide it up into 4 different channels, you pulse each one of those channels and then space out each one of these pulses so that you're able to obtain this continuous monitoring without necessarily doing it with a continuous wave system. So we're able to have this order of magnitude improvement beyond the 10 megahertz, and in this case, since we've got 4 different channels, let's say get up to about 40 megahertz with this solution. And here's an example where we were able to take, so the black line is the on-off keying of the RF signal, and in the continuous wave configuration, we are the atoms are essentially too slow to be able to keep up with the signal. But when you go through the spatiotemporal probe configuration, broken up into these 4 different channels, your pulses and your probe is able to track and stay within and provide all the capabilities that and performance that we want with the system and get up to the 40 megahertz. So then you start looking at, okay, how do we, because in general the customers are looking for something that goes even beyond 40 megahertz. So from that standpoint, we take these multiple channels. We went through this 9-beam configuration. Now we're working on a 16-beam free space configuration using this STM technology, and get beyond 40 megahertz. And so then when you look at the signal that the customers are looking at, you've got ways of being able to change your center frequency and use each one of your modules or each one of your cells to be able to focus on that. And then we could space out the center frequencies so that we're able to cover the entire band that the customer is looking for. So when you look at the quantum ecosystem, in general, L3Harris is focused on 3 different areas. We're focused on the sensing, which is collecting all of this information. Then we're using quantum communications to be able to distribute this information, and then use our quantum processing solutions in order to be able to utilize all of these. So you look at the combination of Infleqtion and L3Harris, and we are able to take advantage of their sensitivity, of their low swap, of the rugged environmental conditions, and we're able to utilize this now in the environments where our customers are looking for. So we specifically have an opportunity where we just won a program of record with a customer for a space opportunity where they are utilizing Rydberg atoms for monitoring these RF signals and being able to create actionable intelligence through this solution. So when you look at also the environment that each one of us is going through, how does this enable what we're doing on each of the areas? So sensors, the things that we're increasing, we're doing a lot of work with our photonic integrated circuits, vapor cells, high vacuum cells, techniques used to be able to control and configure atoms, laser arrays, quantum MEMS, type solutions. We're progressing, with all of these technologies, and this is enabling, because this is all just a money, issue. If we've got enough money, we could solve pretty much, any problem. And so, as we win these programs of record together, we're able to then advance these capabilities, which then advances the whole quantum ecosystem, and we are able to accomplish things that we've never been able to accomplish previously. So it's been a pleasure working with Infleqtion on these opportunities, and we look forward to continuing to progress with additional opportunities with them as well as every one of you. So anyway, any additional thoughts, William?
Yeah, just to add to what Chris said here, it's important to remember that success here in the near term is really critical. And in the sensor modalities we're dealing with here and the applications and sensing and communications, there's a great opportunity to realize quantum advantage. And everything that goes into making these systems better, including not only performance, but size, weight, power, and cost, is going to benefit the secondary systems, right, that will leverage these same technologies. So, more advanced systems, for example, in the quantum compute arena, will definitely benefit from the work done here. It's all neutral atoms. These are vapor cells. These are, eventually PIC-based laser systems. All the techniques that go into making that real and allowing us to transition it, and those technologies themselves are going to benefit, right? Allow us to accelerate what we're doing on the compute side. But we get to realize that benefit today, right? We're getting the benefit today. We're demonstrating quantum advantage of these over classical systems. And I'll leave you on that one note, which is what I started at the beginning of this presentation with, is when you start to think about what just a sensor technology like this can do, and all the constraints now that have been removed that you've been taught, right, are classical constraints, and those have constrained how you thought about designing future communication and sensing systems. You begin to remove that. You start to realize there's things you can do that you never even thought was possible, right? And that's where our thinking is now. As I said, there's ways of now protecting information that classical systems have no possible way of detecting and recovering, because you're now using a quantum device. That is very exciting, and those are things that are realizable today and in the near future. So with that, I'll end.